take a look now at example number 2. Now let's turn our attention to example number 2. Now let's turn our attention to example number 2. So this says that the data in the table below represents the most current marital status of males and females who are 15 years old or older in the US in 2010. And we want to use this data to answer some following questions. First, let's make sure that we all understand how to read the table. Try to think through this here quickly. If I was to ask you how many individuals in this table were males and married at the same time, can you tell how many people that would be? Males and married. Well, that should get me this 62.2 number right here. Notice I can look for the overlap of the males category and the married category. What if I asked for the total number of divorced individuals? Well, yeah, that should get me a value all the way over here in this 23.8. What about if I asked for just the total number of people who were surveyed? Well, yeah, that would give me this value down here, this 242.2. And notice that all those numbers are in millions. So it's 242.2 million individuals. Okay. Of course, being able to read the table is important if I want to be able to start answering these probability questions. Like we said in the last video, every single time we write one of these probability questions, we're going to include probability notation. That's a requirement. And then I will go ahead and actually perform the calculation itself. So let's take a look here at part A. Determine the probability that a randomly selected U.S. resident is going to be male. Okay, well this should be a super easy calculation. If I'm going to go ahead and compute this, I would just start by saying, I want the probability that the person is going to be male. Notice I even already have a little symbol here for that, which is M for male. Now, since I'm randomly selecting U.S. residents, that's going to mean again that everybody has an equal chance of being selected. So I can say that out of the 242.2 million total individuals, how many of those are males? Well, that's super easy. It's 117.8. That's my number down here, total number of males. Now, if I was to go ahead and type this into a calculator, you should be able to confirm that that turns into a percentage of 0.4864. This would be all of the work that I would require if you were doing a question like this. If you didn't include any one of these three portions, you would not be able to receive full credit for the question. So I need to be able to see where you got your number from, obviously what your final answer is, but also that probability notation. All right, let's try part B. Determine the probability that the randomly selected U.S. resident is widowed. Okay, well that's again super easy. Probability that the person is W in the widowed category. So I say, again, there are 242.2 million people to choose from, and the chances that I pick the widowed person, well, let's see, there's only 14.4 million of those people, so the chances are going to be 0.0595. I think that's what you come up with if you crunch that out. So again, super simple. A lot of these probability questions are really straightforward. Now part C ramps it up a tiny bit. Take a look at how. Determine the probability that a randomly U.S. resident, 15 years old or older, is married and is female. So notice here that I'm going to have to include a little bit more in my probability notation. I want the person to be married, so I have a symbol for that. That's MA. And I want them to be female, which has my symbol of F. Okay, now ands again are super easy to calculate here because I just need to go ahead and say that I know there are 242.2 million individuals that I'm picking out of. And where are the people in the table that are married and female at the same time? Remember, that's what and means. I'm looking for the overlap of those two categories. Well, yeah, that's not tough to find, right? That would be like this 62 million. Notice that's females that are in the married category. So that's my 62. If I was to crunch this out, I think I get to a value of 0.2560. All right, how about part D? Determine the probability that a randomly selected U.S. resident, 15 years old or older, is female or is married. Okay, well, let's take a look at this. Okay, so I want probability female, but or married, which is this MA category. Okay, notice this doesn't mean that I want them at the same time, although that's okay. If I think back to what we said with the Venn diagram in the last video, I'm interested in one group or the other group or someone that meets both of those descriptions at the same time. Now, there's just one issue here. If I wanted to go back and use this addition rule that I had at the beginning, I have to note that this rule was only good for disjoint events. That is, I could only use it if A and the B were not able to happen at the same time. Like here, it was impossible to roll a 1 and also a 3 at the same moment. But the question that then we would have down here is it impossible to get someone who is a female and married at the same time? Is that impossible or is it possible? Well, we already kind of saw in part C that it's definitely possible. There are 62 million females who are married. So I cannot use that rule that I had up above. My events are not disjoint. They have an overlap. Okay, well, let's see then if we can slowly try to piece through how we could actually write this out. Well, here's one thing that I might note. Wouldn't you agree that I know out of the 242.2 million people, there are 124.4 million females? Okay, so any of those people automatically meet the first description, right? So those people I definitely want to count as people that meet one or both of the descriptions. Okay. I can also see, though, that there are going to be a whole bunch of married people, 124.2 million married individuals. There's just one problem here. The reason I don't want to just take these two values and add them up for a total is because take a look at how these circled blue numbers were created. I created this blue number at the bottom by taking all of these values and adding them together. And I created this number at the side by taking a different set of values, let's say these values here, and adding those together. Well, doesn't that mean that I counted this 62 million individuals? I counted the overlap one time when tallying down and one time when tallying to the side. So I propose that we could calculate our probability like the following. I'm going to propose that we could say that I want the probability of all the females being selected, the probability of married people being selected, but when I do that, I'll notice again that's going to count this 62 million, that's the overlap, one too many times. And so to get rid of it, that extra time, I'll just subtract it. Let's take a look at how this actually works with our numbers. Again, if I looked at the total number of females, I would know that out of the 242.2, there are 124.4. With married individuals, it was 124.2. And I already calculated up above that there were 62 million individuals that met both descriptions. And since I know I double counted them, I'm going to go ahead and subtract from the total. Right? So I'm adding up all the yellow numbers, I'm adding up all the pink numbers, and I'm subtracting that overlap so I don't double count it. Okay, well, notice that since these are all fractions with a nice common denominator, it essentially simplifies down to just adding and subtracting those numerators together, right? Oops, looks like though I had one quick typo here. This should be 124.4 for the females. 124.4. So this is ultimately what I have, just kind of all over this common denominator. And if I was to add all of those numbers up on the top and do the appropriate subtractions, I would end up with 186.6 out of 242.2. And when I crunch that out, I get 0.7704. So this idea here is telling us how I can use or calculate a probability that has an OR if I have events that actually do overlap. And this is what we summarize into this general addition rule. Here's what it says. If I'm calculating the probability of A or B, if these events overlap, or even if they don't, I can use this formula. The formula was just as what we kind of saw up above. I'll take the two probabilities and add them together, just like the original rule said all the way at the very top. But since these events overlap, and I'm counting that overlap multiple times, I just am going to make sure that I subtract the overlap. So again, what this formula is doing for us is it's giving us a shortcut. It's saying, you want to calculate the left side? Here's a formula for how to do that on the right. Now, let's take a look at how I can use this even if I have events that are disjoint. Take a look at something like Part E. Determine the probability that a randomly selected U.S. resident is widowed or is divorced. Okay, well, I'm going to go ahead and just start writing down what this probability rule would look like. So I would have probability of widowed plus probability of divorced minus the probability of widowed and divorced. Now, again, I should note that I don't need to use this rule because is it possible that the most recent marital status of one person could be widowed and divorced at the same time? Well, no. Again, if it's their most recent relationship status, then you can't have two different one of those. You only have one. So I know that there is no overlap, but let's see how I could use this rule anyways. I know that I'm going to have 3 fractions all over 242.2 million people. Let's see how many widowed individuals there are. Well, widowed was 14.4. Divorced was 23.8. So I'm going to have 14.4 and 23.8. Now, if I go back to the table again, I'd want to look for how many people are widowed and divorced at the same time. Where's the overlap between those two categories? And of course, like we just said a moment ago, when I look at the table, these two rows don't overlap, right? There's no intersection that they have. So I can easily see that the number of people that meet both of those descriptions at the same time is 0. And so I can really just see that while I didn't need to use this formula, and I could have used the original formula that didn't have this portion over here at the back, I don't really lose anything by using this formula because this overlap will just equate to 0 anyways. So if I simplify this up here, I'm going to get a 38.2 over a 242.2 million. And if I crunch that out, that comes out as 0.1577. So hopefully this gives you a good sense of how you can start to utilize some different rules to calculate these probabilities.